Do 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 do. Ice, ice, baby. Hey folks, this is part 2 of a 3-part series on icebox problems. This is the second type of question that you can get. So this is a icebox problem where we have unknown equilibrium concentration. So in these types of questions that you'll get, you will know the equilibrium constant. You'll know the KEQ. And in this case, we know our KEQ reading through this question. Equilibrium concentrations of KEQ is equal to 64.0. The other thing that you'll know is you'll either know all of the product's initial concentrations or the reactant's initial concentrations. It's usually the reactants because we said that when we're setting up an ice box, we generally want to have our products starting at 0. And then we will do some calculations and figure out what happens when we get to equilibrium. So we have the question here initially for the reaction below. We have H2 and I2, the concentrations of those equal to 0.200 molarity. And then we have this general equation given to us. And we're asked to calculate all 3 equilibrium concentrations if KEQ is equal to 64.0. So again, this is the constant of equilibrium. It'll allow us to establish what concentrations exist at equilibrium. So we're going to set up our ice box. I'm going to draw my H2 plus my I2 plus my 2HI. Reacts to produce my 2HI. Let's clean that up a little bit here. Reacts to produce 2HI. And then we're going to fill in, that was a really bad line, we're going to fill in our ice box, ICE. This, and then divide it up. Okay, so what we know from this question so far is that we're starting off with 0.200 molarity of both the H2 and the I2. And what I said in the last video was that if we aren't given a product's concentrations initially, we are going to assume that it starts at 0 molarity. Okay, so now what we need to do is we don't know what these last values will be. We don't know what any of the E columns will be yet. Instead, what we do know is that the KEQ is equal to 64.0. And so what we can do is you can say, well, we know that we are going to use X number of moles, and that will be the change. And we can use the molar ratios to say that, well, if it's a 1-to-1 ratio, the change will be the exact same. If it's a 1-to-2, the one with the 1 molar ratio will happen, and then the 2 molar ratio will be twice as big. So in this particular example, we want to use up reactant to produce product. And so we're going to lose X amount of H2 and I2. We don't know how much yet. We're starting with 0 moles or molarity of HI, and so we want to increase that by 2x. Again, because we have a balancing number of 2 versus 1 and 1 out in front of the I2 and the H2, we are going to change that by 2x. And so what we can establish is what the equilibrium concentration will be, but without all of the numbers. So we have 0.200 minus x, 0.200 minus x, and 0 plus 2x is just simply 2x. So we have values at least assigned for our equilibrium stage here. And so what we can do then is set up our KEQ expression where we have the concentration of products divided by the concentration of reactants. And we can convert that now to our chemical formula, concentration of products, well, we have HI. And because we have a balancing coefficient of 2, we need to square that. And then on the bottom here, we'll have the H2 and the I2. Now, I know some of you immediately are saying, well, why haven't you included this 2 inside of the brackets? And the reason is that we are not doubling the concentration. So if I were to tell you that you're drinking 2% milk, you wouldn't double that amount versus 3% or 4% milk necessarily. You would just assume, okay, it's 2% milk. If I tell you the concentration of HI is 0 molarity, you don't double that. It's just 0 molarity. In the same way that these ones here, even though there's 2 atoms of H, the entire concentration of hydrogen is 0.200 molarity. So we don't include those 2's in the brackets. When we get, however, and let me just give myself some more space, when we get to the next step here, where we start plugging these numbers from our E in here, when we get to this, we're going to put 2x inside the brackets and square it. And then we're going to have 0.200 minus x. And we're going to multiply that by 0.200 minus x. So we'll have to do some foiling for that section. We do need to put this 2 inside the brackets. And the reason is that the concentration of HI is 2 times x. That is just one number. In the same way that I said you didn't include the 2 up here, the concentration of HI is just one number. But for right now, we don't know what part of that number is. It's 2 times something. We don't know what that is yet. And so that needs to get included in this bracket. One of the key things, or one of the areas where I see many students making mistakes, is that when they do this 2x squared, they only square the x. This 2 squared needs to apply to both the 2 and the x. Remember, we said we're talking about one number. If we were, let's pretend that we were to have 2 times, let's say it was 4 in the brackets here, and we were to square that. 2 times 4 is 8. 8 squared is equal to 64. Well, if you did it the wrong way and you only squared the x, or you only squared the 4, you'd end up with 2 times 4 squared is 16. You'd end up with 32. And that's clearly the wrong answer. So this is what we want to do. We want to square both the 4 and we want to square the 2 as well. And that will get us to our correct answer. Just going to get rid of that piece of information to clean this up a little bit for you. Get rid of that, and we get rid of this as well. All right, so we need to square both of those things. And so what we end up with is we end up with 4x squared on the top. And as I said, you need to FOIL out the bottom. So you need to multiply 0.2 times 0.2, 0.2 times x, and then you need to go negative x times 0.2, and negative x times negative x. And when you do, you end up with 0.04 minus 0.4x plus x squared, and we know that that's equal to the KEQ, which is 64. Now at this point, and even actually at the point before, what you can start to see is that every single one of these values here can be square rooted. If you have 0.200 minus x and you're doing that twice, that's the same thing as saying it's squared. And so what we know is that each and every single one of these is a perfect square. And so we can actually just take the square root of each of those expressions and end up with a much simpler formula. And what we end up with here is we end up with the 64.0. Square root of that is 8, as we talked about. So 8.0 is equal to 2x, and we will divide that by 0.200 minus x. To solve for this question, what we'll want to do here is we will want to multiply both sides by this expression. So multiply by 0.20 minus x. Multiply this by 0.200 minus x. We're dividing by 0.200 minus x. And so what we want to do is we want to multiply by it to cancel those two out. So this is gone and this is gone. And we end up with 1.6 minus 8x is equal to 2x. What I'm going to do is going to add 8x to both sides here. Add 8x, add 8x. We end up with 1.6 is equal to 10x. We can divide that, both of these sides now, by 10 to get the x by itself, by 10. And we end up with 0.16 is equal to x. So that's part of our solution there. But now what we need to do, and once we've solved for x, is we need to take that back up into this equation here. And now we need to plug that in for x. So we have 0.200, and we want to minus the 0.16. We have 0.200, and we want to minus the 0.16. And then here we want to go 2 times 0.16. And so what we end up with here is we end up with 0.04, 0.04. Those are both molarities. I'll put a box around those. And then in the last column here, we'll end up with 0.32 as our final solution. And there you have solving icebox problems when we do not know the concentrations at equilibrium, but we're given the initials and the KEQ. So this question was nice because what we did is we started off with plugging in our initial values. We plugged in our changes, and then we set up dummy equations, is what I call them. So the 0.200 minus x, the initial minus or plus the change, whatever that happens to be. From there, we set up our KEQ expression with the square sign. We plugged in each of those dummy expressions that we have into the KEQ. And then from this stage and this stage, this question was a lot easier because we had perfect squares. And so this question did not require the quadratic formula. It was a lot easier to solve for. We ended up solving and getting 0.16 is equal to x. And then from there, we plugged that 0.16 back in. If you wanted to check your equilibrium expression to see did you do all your math right, you could plug each of these numbers in these spots here. So you'd square the 0.32, take 0.04 and 0.04, and what you should find is that equals 64, and that's how you can confirm that you've done the question correctly. That is how to solve equations, equilibrium expressions, when we have perfect squares and when we have unknown equilibrium concentrations as well. Hope that made sense, and we'll see you in the next one.